Okay. So hi everybody. Hi team. Thank you for accepting our invitation. So today with us we have Team Ryck, which is a PhD student from ATH in Zurich, and he will talk about mathematical guarantees for physics-informed machine learning. So thank you all for attending this seminar, and so please, you can start whenever you want.
Okay, thanks a lot, Anna, for the kind introduction, and thanks again for the invitation. It's very nice to speak here today. So yeah, I will talk a bit about what physics-informed machine learning is exactly. I will start with that. And then I will talk a bit more about how to prove mathematical guarantees for it. And this is sort of what I've been working on throughout my PhD in the last bit over 3 years now. So I'll first argue that there are 4 central questions one needs to answer to provide some mathematical guarantees for it, and then I'll give an overview of the results we have proven to answer those 4 central questions. So my talk of today is essentially like a summary of, I think, around 5 papers that have appeared in the past years. And of course, I didn't write them all by myself, so I need to thank my collaborators to start with. So first of all, my PhD supervisor here at ETH is Professor Mishra. And then, there's some colleagues from ETH, like Roberto Molinaro, Emmanuel Bisnack, then Professor Jakta from Brown University, my former colleague Samuel Landthaler from Caltech, and Florent Bonnet from Sorbonne University. So let's move on to physics-informed machine learning. So in physics-informed machine learning, we want to approximate solutions to PDEs with a neural network. And this PDE, it can essentially be anything. So in my talk, I will adopt this very general PDE setting. So just imagine you have some differential operator L, that's the curly L there, that describes your PDE. So for instance, like in the blue example below, like for the Poisson equation, this would just be the Laplacian. And then you have some boundary conditions that are described by some boundary operator B. So if you just have Dirichlet type boundary conditions, B would just be the identity. If you have Neumann type boundary conditions, B would be the first derivative. And for simplicity, we imagine that this B encompasses both like the spatial boundary conditions as well as the initial conditions if you have a time-dependent PDE. And for this talk, I will focus on just scalar solutions. So we assume that U maps from our domain, which can be just your space domain, or also might also include the time interval, but it will map to R. So it will be a scalar solution. And then our task will be, well, there are 2 tasks one can consider. My talk will mostly be about the first task. And the first task is just, okay, given some fixed, so there I wrote U0, so some fixed initial conditions, some fixed source function, everything is fixed. In this setting, we want to approximate the true solution of the PDE. So we want to find a model U theta. So I'll always write the model as U theta, where theta are the parameters of the model. And we just want to find a model that approximates the solution to the PDE well. A second, way more difficult task would be to approximate the whole solution operator of the PDE. So what is a solution operator? What's an example? For instance, for a time-dependent PDE, you might want to map your initial condition, which is a function already, to the solution of the PDE at a later time. So in this case, you want to map a function to a function, so that's an operator, or alternatively, maybe you want to map the source function f to the solution of the PDE. So in this case, that's something we call the solution operator. And also in this case, you want to find a model, which is now also an operator, to approximate this solution operator. So this is the setting we are in. And so for the first task, the most simple task, what is our ansatz space there? Well, it could be anything, could be any model you can think of. Of course, in classical numerical methods, there's a lot of linear models around, which are just linear in terms of the parameters, of course. So you just have a bunch of functions and you want to learn the best combination of coefficients for those functions to then sum them. That will be your model. And examples would be like spectral methods, finite element methods. You could use radial basis functions, random features models. Those are all examples of linear models. Of course, nowadays, it's also quite fashionable to use nonlinear models. The most famous example being neural networks, of course. So I'll also focus a bit more on neural networks throughout my talk. But also Gaussian processes could be used to approximate solutions to PDEs. And then when we move to task 2, so that's where we want to approximate the solution operator, there are something called a deep operator network, a deep O-net, which can be used for that. So that's a neural network that allows to map from functions to functions, or also Fourier neural operator is another example of such a model that allows to do operator learning. And in case you're not familiar with neural network, because it might be important later on through the talk, I'll just give a quick definition, the mathematical definition of what a neural network is. So a neural network, in essence, is just a composition of affine maps on the one hand and activation functions on the other hand. So given your input vector x, what a neural network does is it multiplies it with some matrix. It adds a vector, so that's your affine map. And then you just pass it through some nonlinear function. That's what we call the activation function. And then we repeat this a couple of times. So you again apply some affine map. So those are the ALs here. You again apply some activation function. You repeat this a couple of times, and you have a neural network. And the parameters of this neural network are the entries of those matrices and vectors of the affine maps. And whenever I will talk about the neural network in my talk, I will mean neural networks that use the hyperbolic tangent as the activation function. This is just a small detail. It could be any other smooth activation function, really, but for simplicity, I'll stick to hyperbolic tangent activation functions. Okay, good. Then let's move on to what physics-informed learning actually means. So remember, we want to approximate the solution of the PDE, U, say in L2 norm. So if we would adopt the supervised learning paradigm, that would correspond to using the following L2 loss, right? So you just want to minimize this loss. You just want to find a U theta such that this loss is as small as possible. Of course, the problem here is that this loss depends on U, and U is exactly what we want to find. So it's a bit weird. So what you could either do is maybe you have measurements, so you can approximate this loss here using measurements. Or what people also did quite often was to do some classical numerical simulations to already get an approximation of U on a very coarse grid, and then use those approximations to build an approximation of this loss function. But then the problem is you still need to do those classical numerical simulations. And for instance, in high dimensions, those might be very expensive. So that's not really the most efficient approach. So that's why people try to come up with a different approach to try to come up with a loss function that doesn't depend on U. And this is where physics-informed learning comes in. It's based on a very simple observation that for your true solution, for U, you will have exactly that L of U equals F, because that's just the definition of your PDE. This will hold exactly. So the idea is, let's just replace U with U theta, and then let's try to find a model U theta such that L of U theta is approximately equal to F. Yeah, because we know if U theta would be the exact solution, it would be exactly an equality. So let's just try to find something for which this equality approximately holds. And then this is the basis of physics-informed learning. Why do we call it physics-informed learning? Well, because now in our loss function, we will use the PDE, and the PDE, of course, describes the physics of the problem. So we want to find a physics-informed loss function such that if we minimize it, it's a good approximation of the true solution. And for this, we need to define something we call residuals. So we define a PDE residual, which is literally just what I said before. So it's L of u theta now minus f. So remember again, if we would put our u in here, if we would put the true solution of the PDE here, the residual would be 0. Similarly, the spatial boundary residual, which corresponds to your boundary conditions, here Dirichlet boundary conditions. And if you have a time-dependent PDE, you also have a temporal boundary condition, which corresponds to your initial condition. So it just measures how far away your model is from the true initial condition here and boundary condition here. And then we just square it and we integrate it over the whole domain. And we do the same for the other residuals. And then this is our new loss function. So this will be the central physics-informed loss function throughout the talk. As you can see, it doesn't depend on u anymore. So this we can just calculate at any time. And we also see if we would fill in u here, so if we would fill in the true solution, we will get exactly 0. So that's sort of why we think it's a good idea to try to minimize this loss function to make it as close to 0 as possible. Of course, there's a bunch of integrals in there. If you have a complicated model, it might not be feasible to calculate those integrals exactly. But okay, I'll jump to that later. First, this slide here. So just as a quick example, let's look at the Laplace equation, just Laplacian of u equals 0 with Dirichlet boundary conditions. So this whole formula that I just said before now reduces to this. So yeah, this is the PDE residual in this case, and this is your spatial boundary residual. Of course, for some PDEs, you might not find, there might not be a strong solution of the PDE. So in that case, you might be interested in finding weak solutions. So what is, again, the definition of a weak solution of the PDE? You just look at your PDE formulation, you multiply both sides with some smooth test function, and then by integration by parts, you move some of the derivatives from your true solution to your test function. And this is also something we can do to build another loss function. So this is like if you multiply this with a theta k, so theta k is a loss function, you do integration by parts, then you come up with a term like this. And then if you choose a bunch of test functions, so a bunch of theta k's, and you just sum those, then you will again have a well-defined loss function. Or in the case of the Laplace equation, you could also directly use Dirichlet's principle, which says that you can just take your test function to be equal to your model, and then you end up with this, this physics-informed loss. So these are like 3 variants of physics-informed losses that one can use in this case for the Laplace equation. But we will focus on the first loss in this talk. Good. As I was saying before, if you have a very complicated model u theta, it might not be feasible to calculate this integral. So what do we do in practice? We replace the integrals by sums. Yeah, that's quite easy. So we call our training set S now. So the training set is just a bunch of grid points. So in this case, it will be grid points in your interior of your domain. Of course, for the boundary residual, you'll take grid points on the boundary of your domain, and so on. And then this J, this will be our new loss function, the one we'll actually use, and of course depends on the parameter of your model, as well as this training set. And then what we do is we use some gradient descent type method, some often stochastic gradient descent type method to minimize this loss function. And then the parameter that comes out of that is what we will call theta star. So u theta star will be the model that we're looking for. And then just a bit of notation for the rest of the talk. So this physics-informed loss with the integral in it and not with the sum is what we'll call the generalization error, because it measures how well it does on the whole domain. And this discretized loss is what we will call the training error. So the training error is something we can measure during training. And of course, it only measures how well the model does on some grid points. But we, of course, want that the performance generalizes to the whole domain. So that's why we call this a generalization error, because it measures how well the model does on the whole domain. And then finally, ET star is just your training error for this specific choice of your parameter. So that's the training error corresponding to your trained model or your chosen model. Okay. So this is physics-informed learning in a nutshell. Maybe good to see whether there's any questions about this before I continue.
If anybody has questions, okay, you can go on.
Okay, good. So with this in place, let's talk about what we actually want to do, what we want to prove. So we now have this physics-informed loss, which measures something, but it doesn't measure the L2 error anymore. But in the end, we still want that, U theta is a good approximation of U. So we're still interested in having a small L2 error. How do we prove this, that in the end, the L2 error will still be small? Well, there's 4 questions we need to answer. The first point is that we need to have some kind of guarantee that if we minimize our physics-informed loss, then also the L2 error will be small. So we want to have an inequality of this kind, because this will say that if our physics-informed loss or generalization error is small, then also the L2 error will be small. So this kind of stability is a first necessity for physics-informed learning. Because if we don't have something like this, then okay, maybe the physics-informed loss will be small, but if the L2 error is still large, then that's not of any use to us. Then,
Okay.
sorry.
What is alpha over there? Alpha.
Oh, alpha is just some coefficient. So that's like the exponent of this. So it doesn't have to be, E star is smaller or equal than a constant times the generalization error. It could also be the generalization error squared or the square root of the generalization error. It's any positive
Number. Okay.
Yeah. So, but it might depend on the PDE you're looking at.
Yeah, I wanted to understand this positive and negative.
Okay. You can go on.
Okay. So with this assumption in place, we can decompose the error as follows. And the first contribution on the right-hand side is this term here, this term, which is something we call the approximation error. So what this does is it says that, okay, we now have some other parameters, some other model, some theta hat. So this is not theta star. And we can choose it whatever we want it to be. So we want this to be small, of course. So what this question actually says is, does there even exist a model in our model space for which we can minimize this physics-informed loss? Because, I mean, that's not guaranteed. Like if your model space would be the space of constant functions, then of course it's very likely that you won't be able to minimize your loss function using just constant functions. So then the approximation error would still be very big. So the second question is like, how small can we get this? How small can we get this approximation error? The third question is about the generalization gap, which is what we call the difference between the training error and the generalization error. And this question essentially is, how well can we approximate the integral in the physics-informed loss with the sums, because we approximated the integral with the sum. So this is a very classical question. This is the easiest question of all of them. And then finally, we have the optimization error here. So this just compares how well or how small the training error of our trained model is compared to the training error of the model we chose here for our approximation error. Because we might know that there is this very good model in our model space and it can approximate the solution very well. but maybe we can't reach it using gradient descent. Maybe gradient descent will get stuck in some local minimum, and then the solution, the model might still perform bad. So we want that this is small as well. So this is what we call the optimization question, or the question related to train. So for the rest of the talk, I will go over those 4 questions and tell you when you'll get an affirmative answer and maybe sometimes not an affirmative answer. So the first question was about stability. So first we want to see when we can prove an inequality like this. And for many PDEs, this is actually not too hard. It's just like a direct consequence of PDE theory. For instance, like if you look at Evans or any other book on, you know, PDE theory, you will find those type of inequalities. For instance, under the assumption that like your linear differential operator, I can't seem to select it here, but you have when you have a linear differential operator with a bounded inverse, then such a stability result will automatically hold. Or similarly, if your differential operator is nonlinear, but you can linearize it and it's well-defined and it has a bounded inverse and so on, you will automatically get the stability. So that's quite nice. To give a concrete example, so loads of formulas here, but it's not too much actually in the end. So this is just an example of what a stability result would look like for the semi-linear heat equation with some source function f, can be anything, of course, it still has to be square integral and so on. And we also assume that f is Lipschitz constant. And in this case, our model is, we call our model V. And then we see that the square of the L2 error that our model V makes compared to U can be bounded in terms of the squared L2 error of our PDE residual, the square of the L2 error of the residual related to the initial condition, and then also the L2 error of this boundary residual. So this is exactly what we want. It says that if we minimize all those residuals, we will get in the end a small L2 error. And this is, of course, this can be bounded in turn by our physics-informed laws. So this exactly proves our stability results. Unfortunately, these results don't always hold. As you can see here, our constant for this case depends on the C1 norm of U. So it depends on the derivative of U. And there are some PDEs, such as conservation laws. For instance, if you have like some viscous burgers type of PDE with some viscosity constant nu, if your nu gets very small, then your C1 norm of your true solution will grow something like this, as 1 over nu. So this will get very large. So in this case, we do have an inequality like this, but this constant C will explode essentially. So this won't be very useful. And then you might have to look at other loss functions. So this is why I already talked a bit about this weak loss function. So we made an adaptation based on physics-informed neural networks, which we call weak physics-informed neural networks, to better approximate solutions of scalar conservation laws. And then we also proved that if we use this adapted loss function for scalar conservation laws, such as Burger's equation, then we're back in business, then we can still prove some stability. Another example is Hamilton-Jacobi-Bellman. So this is not our result, but a very interesting result that says that there are instances of the Hamilton-Jacobi-Bellman equations where your PDE residual is as small as you want it. It's smaller than some epsilon. The boundary conditions are exactly satisfied, so sounds very good. But yet still, the L2 error can be arbitrarily large. So this is the worst case scenario for physics-informed learning, because we're just trying to minimize this, and then we're essentially hoping that this will be small. So in this case, it won't work. So don't use physics-informed machine learning to solve Hamilton-Jacobi-Bellman type equations, because it has been proven that it might not work. A third example are some other type of adaptations of physics-informed neural networks. So in case I didn't say in the beginning what physics-informed neural networks are, they're just neural networks where you use the physics-informed laws, just to make that clear. So what this here means is that you might know domain decomposition from classical numerical methods, and people have combined this with physics-informed models. So what they do is instead of finding one model on your whole domain, they will divide the domain into subdomains, and then they'll try to find a model that performs well on each of those subdomains. Of course, then you need to make sure that your models agree on the interfaces of all the subdomains, and for that you need some other additional terms, and there are multiple ways how to introduce those terms. And one way to do it is using extended pins, and another way to do it is using conservative pins. Both methods have been proposed mainly based on experiments, and in the experiments it worked well. But actually, we have proven that if you use those extended pins, then you might get into trouble. You might end up with a situation like this. So there might not be stability if you use this type of method. Whereas for the other method that's called C-pins, we have proven for many PDEs that you will get stability, like this type of stability. So regarding stability, it holds for many PDEs, but there are some exceptions. So as a practitioner, you always need to be careful that physics-informed machine learning makes sense in the end. Okay, then moving on to the approximation error. So this question relates to, does there even exist a model in our model space for which the loss is small, right? Think of the example I said before with the constant functions. If you would use constant functions, then there probably isn't a model that will make the loss small. And then additional questions you might want to ask is, okay, if there is a model in our model space, how large should the model be? For instance, if you're using neural networks, how large should the neural network be to get a certain error? You know, we want to make sure that we don't need a model that is as big as the one that OpenAI uses in their large language models, because we can't run it on our computer. So we want to make sure that the model can be sufficiently small. In particular, for high-dimensional PDEs, it's very important. We want to make sure that we can overcome the curse of dimensionality. What is the curse of dimensionality? This means that the number of parameters you need in your model scales exponentially in the input dimension. So if your input dimension is very big, then you need exponentially many parameters, and this will become infeasible or at least very costly. Okay, so what is the most basic approach one can do here? One can, of course, think about this, and okay, so there's this PDE residual here. There's a -f missing, by the way, sorry for that. One can very easily prove using the triangle inequality that one can bound this in terms of a higher order Sobolev norm. Because what you're doing here is you're just saying, okay, your model approximates your true solution well, and the derivatives of your model also approximate the derivatives of your true solution well. So as a result, the PDE residual will be small as well. So this is something very easy to do. Of course, now we need to know that we can make this small, because if we can make this small, we can make this small, and then we have answered question 2. So there's for classical type of basis functions, for instance, if you have a Fourier basis, then this is known that you can make this as small as you want. So this is not a problem. For neural networks, it's a different story. You might have heard about universal approximation theorems for neural networks. The problem there is that those are all stated in either L2 norm or L infinity norm. And here we need an approximation result in a Sobolev norm, a higher order Sobolev norm. So up until a couple of years ago, there weren't really any results available on this, but now there are some more results. So this is an example of what a result of this way would look like. So assume you have a function that we want to approximate that is like Sobolev regular of order S. Then our result says that there will guaranteed be a 10H neural network with only 2 hidden layers of width n to the power d, such that you get the following error estimate. So this is exactly the error estimate, or exactly the convergence rate you would also get for like Taylor expansion and so on. So this is what you would expect, except for this additional logarithmic factor. And then the nice thing about the results is also that all the constants here are explicitly known, because very often people throw away the constants, and then if you look at the proof, the constants are actually like 10 billion. And then the error estimate is not that useful in practice, of course. But the result isn't perfect either, because the problem here is that we run into the curse of dimensionality. So if D is very big, this theorem will tell us that we need a lot of parameters, a very wide neural network, which might be infeasible. So it would be nice if we can overcome this. The other problem, so to say, is, like I said before, actually a lot of the known results are mainly on the LQ error, so L2 or L infinity error. So we have a lot of results that say neural networks can overcome the curse dimensionality for this type of PDE in the L2 error or in the L infinity error. Is there then really nothing we can do to use those results and like elevate them to physics-informed losses, to Sobolev losses? So that's another question. And then the other problem is, so it's not the case for this year, but a problem is that people have been proving these type of results very much on a case-by-case basis in terms of PDEs. To give an example, we also had a paper a couple of years ago that was like, okay, physics-informed neural networks overcome the curse dimensionality for linear cohomograph PDEs. And other people have proven the same result for a different type of PDE. And these were all separate papers just because it's quite a lot of work to prove those things. It's like 30 pages every single time. So this is a lot of work. So like what people have essentially been doing is they want to prove these type of approximation results for very different classes of PDEs. So to visualize this, I have PDE 1 to PDE 6 here. And they also want to do it for different type of loss functions. So here I call this LQ error, or so this is L2 or L infinity, a supervised loss function, so supervised neural network. So for this, a lot of results are available. So when there's a check, it essentially says, okay, for this type of loss, for this type of PDE, there's an approximation result available. For physics-informed neural networks, there are some results available, but much less. So only in the low-dimensional setting, of course, you can use this theorem here that I showed you, but there's nothing in higher dimensions. So there's much less results there. And then recalling our task 2 from the beginning about operator learning, also in those scenarios, we want to prove those type of things. And because the fields are so new, there's essentially no approximation results available whatsoever, even though it's quite important, because if you can't do an approximation result, then it might be useless to do this type of framework or method. So this was essentially the status quo a couple of years ago. And then we were also doing it like this. And then after a while, we essentially noticed that we were always doing the same thing in our proofs. So we tried to generalize it a bit further. And we essentially said that, okay, if you can prove it in the simplest case, so the simplest case is a supervised neural network. That's the easiest thing to prove. So if you can prove it there, and if you can verify a couple of assumptions and those assumptions hold, then our generalized results essentially give you for free an approximation result for physics-informed neural networks, or an approximation result for operator neural networks, and so on. So we essentially made it easier in a way to prove these type of results. So now what you still need to do is you need to prove something for supervised neural networks, which like a lot of people have already done. You need to check some assumptions, and then all of a sudden you get way more checks in your table. Yeah, and then the other thing that we noticed is that the method we were using actually didn't depend as much as the PDE, on the PDE as we initially thought. So there are some more assumptions that one needs to check, and then so you prove it for one type of PDE, you check the assumptions, and then you essentially get an approximation result for a different type of PDE. So to give you a flavor of a kind of results that was in this paper, so let's go over it together. So say you want to make your physics-informed loss smaller than some epsilon, which you said before, and for simplicity, assume that your domain D is either rectangular or smooth. And then here comes the thing. So let's assume we have a time-dependent PDE. Then we need to be able to prove ourselves that for any time in our time interval, there is a neural network that approximates the solution of our PDE well at that single time in L2 error. So we need to prove that this holds. But those networks, so this can be a different network for every time. We don't need to prove that the result holds on the whole time interval. So we don't have to prove that there is a neural network that also takes the time as an input that does well. This is also something that the result gives you for free. And then the second thing you need to assume or make sure is essentially what we already said a couple of slides ago, that you need to be able to bound your PDE residual in terms of a higher order Sobolev norm. If those two things hold, then our result tells you, okay, there will actually exist a neural network that now also takes time as an input, for which your physics-informed loss will be small. So I wrote it a bit different here. So again, there's a minus F missing here probably. So this is your PDE residual, and then this here is the L2 error, the boundary. So also this will be small. And then this delta here is a function that will go to 0 if epsilon goes to 0. Of course, in the paper, we exactly quantify this convergence rate, but just for the size, I made it a bit easier here. And then it's very, very nice because as a corollary, we get, for instance, again, that physics-informed neural networks overcome the curse of dimensionality for a lot of classes of PDEs. For instance, those linear homograph PDEs. A famous example of those are just the Heat equation or the Black-Scholes equation. Very interesting PDEs are in there. But also for nonlinear parabolic PDEs, such as the Alenkane equations, we find that pins can overcome the curse of dimensionality. Okay. See, I'm running a bit short on time. How long was the talk supposed to be? Can someone confirm? Was it 45 minutes or?
Yeah, also 40 as you like, 40 minutes is okay.
Okay. I'll try to go a bit faster. That shouldn't be a problem.
Don't worry, I mean, also 45, 50 is okay, don't worry.
Okay, yeah, it won't be 50, no worries. So yeah, let's just skip that slide. So let's close off the approximation chapter here. So we've essentially found that in most of the cases, you can actually approximate, you can actually affirmatively answer the question about approximation. Just again, for those scalar conservation laws, there, of course, it doesn't make sense to approximate it in Sobolev norm because solutions of conservation laws might have jump discontinuities. So there again, we need to use this weak physics-informed neural networks framework, and it's going to be a bit different. And then the next question was about generalization. As I said, this is the easiest question. It's essentially just a question about how well can we approximate our integral with the sum. And then just look at this final line here. Like this is essentially just numerical integration, just like your standard Gauss quadrature or something like this will give you an approximation rate like this. And this essentially solves it. So this essentially affirmatively answers our question about generalization. If you use a random training set, you might think it would be like Monte Carlo integration, but the tricky thing here is that our function now also depends on the training set because it's trained on random points. So you need to be a bit more careful. There's some assumptions here, but what I want you to look at is that this is so the expectation, because you have a random training set now, expectation of a generalization error. Here's the expectation of a training error. And then essentially what this is essentially just square root of n. So this is exactly what you would expect from a Monte Carlo type of estimate, just with logarithmic correction here. But then what the interesting thing about this generalization question is that different PDEs will lead to different convergence rates. For instance, for the Navier-Stokes equations, we find that we need way more grid points in the interior of the domain than we need on the spatial boundary or than we need on the temporal boundary. Whereas for instance, for a high-dimensional heat equation, if you use random training points, we find that you actually need way more points on your spatial boundary than you need in the interior of your domain. So these type of convergence rate actually tell the practitioner maybe you need more points there than you need points there. So this is how one can use our results in practice as well. And then the final error, as I said, is a training error. So this is the question, okay, how in practice can we actually make our training loss small using gradient descent, using stochastic gradient descent? And then, especially for physics-informed neural networks, this can be quite hard. So this is not something we did. This is something people in the US did a couple of years ago. They tried to solve just a linear transport equation on a periodic domain. So in the left column, and the figures on the left, you see the exact solution. So they increased beta, they increased the advection speed, and as you see, of course, the solutions become steeper in this view. And on the right, you see the approximations using physics-informed machine learning. For small enough b, it works well, but you see for larger betas, it doesn't work at all. Like the neural network will just converge to some trivial solution for most of the domain, and it will be an incredibly poor approximation. So we affirmatively answered the 3 questions before, but now it all breaks down essentially in the training. So we try to investigate this. Don't look at the formula here, but let me summarize it for you. So what we did is we looked at gradient descent, the gradient descent that corresponds to physics-informed machine learning. And we proved that you can approximate it using just this linear relation. And as you can see, this matrix A is the central component of it. And this here is just your learning rate, or the step of your gradient descent. And what we've proven is that it will converge to this theta here. And the convergence rate will depend on the condition number of this matrix A. So the bigger this condition number is, it means the slower your convergence will be. And now, what is this matrix A? It's actually the condition number of this matrix A is equal to the condition number of an operator. And this operator is the composition of 2 operators, and the first one is the Hermitian square of our PDE operator, the Hermitian square of the differential operator. So what's the Hermitian square? This is just the composition of the adjoint of the operator composed with the actual operator. So it's a bit of the square. On the other hand, this operator T depends only on your model. So you can sort of decompose this matrix A in terms of the PDE that you want to solve and the model that you're using. And of course, now what we want to do is, well, it would be ideal if we can choose our model in such a way that this operator T is sort of the inverse of A. Because if T is the inverse of A, and of course, this must be well-defined and so on, but if that's the case, then this will approximately the identity. And then we will get a condition number of approximately 1, which is the best possible scenario. And of course, if that's the case, then we will get a very fast convergence rate here. So how can we do this in practice? Actually, what you just need to do is you need to linearly transform your parameters in a smart way. So you just need to replace theta by a matrix multiplied with theta, and then you will automatically end up with a preconditioned matrix A, which will have a better condition number. Of course, the question then is, how do you choose this matrix P? And this is then again equivalent with directly preconditioning your gradients in gradient descent. So these are two equivalent approaches one can do. Then also the interesting thing is that one actually can look again at all the methods people have proposed in the past to improve training of physics-informed neural networks. And then using like this machinery, we can actually realize that all those methods were just meant to precondition the matrix A or precondition this operator. For instance, if like this is our physics-informed laws, there is this parameter, this weight parameter lambda here. As you might imagine, this might have a big influence on the convergence rate. So what we now can just do in practice, we just minimize this. So we can calculate the condition number of this matrix A for many lambdas, and then we just choose the lambda for which this is minimal. So we just choose a lambda for which we will get the best convergence rate. And then very similarly, one can make considerations about using hard versus soft boundary conditions. One can realize that second order optimizers, what they're actually doing is they're just preconditioning the gradient, which is again connected to what I said here. And also domain decomposition can also be seen as a form of preconditioning. For instance, if we go back to this, example here, we find for this example that the condition number of the matrix A depends on the square of the interaction speed, which is what we see here. But if one does domain compositioning, which in this case is just splitting your time interval into n sub-intervals and training a network on each sub-interval, then one can reduce the condition number. Then the condition number will just be something like beta squared over n squared. So if you take n big enough, then your convergence will be much faster again. And this is also something one calls causal learning in the literature. Okay, so this is where we're at regarding optimization. So we have made some start, but it's still a very hard question to solve. But let me quickly summarize the mathematical guarantees we've proven for the three other questions. So I argue that stability holds for many PDEs, but not for all PDEs. Remember, Hamilton-Jacobi-Bellman equations were an important exception there. And when it holds, it's often just a result of PDE theory. It's not very model dependent. Then regarding the approximation error, this usually follows from error estimates in Sobolev norms, but we've also proven this result on generic bounds, where we connected many type of approximation results. And then the nice thing about the generalization bounds was that they sort of recommend practitioners to use certain training set sizes, or they recommend to use certain ratios. And then finally, as I told you, the optimization currently is the biggest challenge. And what our theory shows is that preconditioning is really necessary, but this is still very much ongoing work, I would say. And this then brings me to the end of my talk. Sorry for going over time a bit, but hopefully you enjoyed it. And if there's any questions, I will be happy to answer. Thank you.
Okay, thank you, Tim, for the nice presentation. So time for questions. Any questions from people in presence? Okay, this
can you ask him to go to the generalization error, and then he mentioned some quadrature to get the final estimate. So can you just go through it, and can you hear or not? No, I don't think so. You can hear me, right? No.
Can you hear Tim?
I can hear something, but not everything. So if you could repeat the question, maybe, or
Browser or raise.
Tim, so you had this generalization error, right? You had this. You mentioned some quadrature formula to get this final estimate. So can you talk about it? Like, what are the steps here? And what quadrature are you actually talking about? Where is the integration here?
Yeah, so let me go back to the definitions maybe. So here I define the generalization error as our physics-informed loss, which is formulated in terms of integrals over the domain or your boundary, or yeah, your domain without the time interval, right? So this is all formulated in terms of integrals. But if you have a neural network, you can't exactly calculate those integrals. So we replace those integrals using finite sums here. So in a generalization error, what we just want to answer is, okay, are those integrals here well approximated by those sums here? And then the usual answer is yes, as long as you sum over enough grid points, it will be a good approximation. So people just use some kind of Gauss quadrature. In practice, they just choose some grids, and then yeah, approximate integrals on that grid using sums.
Okay, yeah, okay, I see your point. So the other question here is that when you had this decomposition of error, I think Yongjung Shin also has in its paper a similar thing like generalization plus optimization plus approximation error.
Yeah.
Uh, is there any difference between your decomposition or his decomposition? It's been a long time. I've not seen Yongjung Shin's paper in a while, so I forget. Sorry.
I mean, I don't remember or know their results explicitly, but I mean, this is not a new error decomposition. So this is not our contribution. This is very classical in the field. So it's probably the same or equivalent at least.
Okay, stay on this slide. Stay on this slide. So theta is actually the the parameters of this neural network, and now alpha is going to be a positive number, right?
Yes. Yeah.
So if I increase the neural net the width and the width or whatever the layers, that's going to blow up.
Sorry, what's going to blow up?
If theta becomes large,
Yeah.
so and alpha is a positive number, so
Yeah.
theta, if I keep increasing my theta, if I let my theta go to infinity, that blows up, right?
So this is the error though. It's this alpha corresponds to this whole thing.
Yeah, but the error, okay, the error, okay, so the error is okay, unless you're commenting that E of G of theta star is always less than 1, this is going to blow up. You see
Yes, but you're trying to minimize this. So if you increase your model space, you will actually be able to decrease your error. So if you increase the size of this theta, actually this will decrease.
Yeah, but we need, okay. Okay, anyway, okay, let's go to something else now.
Okay.
I forgot my question. Anyway, if I recall anything else, I'll come back. But meanwhile, if somebody has something to talk about,
Yeah, we can go on with other questions.
Yeah.
Then if you remember, we can come back. Okay,
So,
Mario. Also,
So, hi team, thank you for the talk.
Right.
You go on the slide, I think 23, 24, when you talk about neural tangent planet.
Yes, let me quickly go there.
The preconditioning, yeah, here we go. So this is valid, I mean, your results are valid only in the infinite width limit, while you approximate the tangent kernel constant, right? So it's valid any results when the network size is smaller.
Yeah, so it's not necessarily only valid in the infinite width case, but we do need the NTK to be approximately constant. And as far as I know, you can only prove that if your network is wide enough.
Yeah, of course.
Of course, if it happens to be, if the NTK happens to be constant along your optimization trajectory, then this will also hold. So the nice thing here is that if you have linear models, then your tangent kernel will be constant by definition. So this holds very well. So This is initial work. So for neural networks, it's not as, the theory is not as nice as we hope it will be at some point. But so the examples we use are mainly also for linear models where these assumptions hold exactly. But it's a very good point.
Okay.
Yeah.
And what do you mean that causal learning, it's kind of a conditioning mechanism? Because I understand the split, right? The time marching and that stuff I understand, but why causal is considered a preconditioning as well?
So causal learning in this context is, it essentially does this. So when you have a causal learning loss for pins, you will first try to get a very good approximation from 0 to t over n. And then once you have a good approximation there, you will move on to the next one and so on. So there you essentially also, you're still using only one neural network instead of n different ones, but you're still training it on much smaller domains. And because you're training it on a smaller domain every single time, it will still reduce your condition number.
Okay. Yeah, because in the splitting, you first minimize on that stuff and then move on. In causal learning, actually, you're waiting. So it's not less risk.
Yeah.
While minimizing the first stuff, the other one are 0, I think. Correct me if I'm wrong.
Yeah. So it is different from splitting, but in practice, it will still be some form of preconditioning. So you might not get exactly the same reduction of the condition number, but still you'll get a reduction.
All right. And last question, because I saw that you were the author of WeakPin. DPin, variational one, the one of the Kaniadakis group. Do they have similar guarantees as the WeakPin? Because I saw that you approximate the test function with a neural network.
Sorry, which paper? I didn't.
VPin, variational pin. So
it's the one, it's the one case that you showed with the weak PDE. That's
Yeah.
basically VPin variation. Just basically weak PDEs. That's all.
Yeah. So the weak pins that I talked about are not the same as the V pins that the group of Kaniadakis has.
Okay.
I don't remember whether they have any stability results or approximation results, if I'm being honest. I don't remember.
Just a curiosity. So in the weak one, you approximate the test function with the neural network, right?
Yes, exactly. That's the main difference. Yeah. So
Sure.
they use an approach more like this one here. They choose a fixed set of test functions, whereas we just have one test functions, but then we let it be a neural network, and then we do some kind of min-max optimization to let the neural be like the neural network be the worst possible test function.
That's a kind of adversarial training approach, more or less.
Yes, very much. Yeah. Good point. Thank you.
Okay, other questions, curiosities?
So, so in the approximation error that you showed, that in the first part of the decomposition, the first is the approximation error. Now, I didn't see Chen and Chen's work. So, are you using any? Are you aware about this work from Chen and Chen?
I think so. Yeah.
He has he gives the for the neural network, he gives the approximation error, right?
Yes, yeah. If we're thinking, maybe I'm mistaken, but I think the difference is that we have some exact convergence rates, and I think they mainly prove the convergence without the rate. Is that correct? Is that the paper you?
Yeah, more or less, but I'm not sure what norm they are using because I didn't really pay attention for that. But anyway, so this result is for a shallow network. Does it hold if it is a deep network or no? Did you empirically verified it, or because I know that if you have a deep network, that the nonlinearity, the analysis gets a bit issue. But did you empirically verify it or not?
Do you mean specifically for this theorem here, or?
Yeah, for this theorem here. So if I increase the hidden layer from 2 to 4, let's say, did you empirically verify that something like this will hold or not?
Yeah. So what this theorem says is you need sort of at least 2 hidden layers. So 1 hidden layer won't be enough according to our results to approximate it efficiently, but you can have more hidden layers. And then we also in the paper we also did some experiments to verify this.
Okay. All right. Thank you.
Thanks for your question.
Okay, are there other questions also from the online part? So if yes, you can just activate your microphone and ask. Okay, it seems not. So we thank again Tim for this nice talk.
Yeah, thank you for the invitation. It was very nice to speak at CISA.
Thank you, Tim, and thank again people attending the webinar. And see you the next. No, maybe not the next Friday, but
Yes. Yeah. Thank you. Have a nice weekend, everyone.
You too. Bye.
Bye.
Thank you. Bye.
Bye.